Okay, morning everyone. Believe it or not, we are at the third waypoint for the term, which is kind of crazy to think. It feels like the term really just started not too long ago. So our steel knowledge is loading. We're about 33% of the way through the course material, or at least we will be after the lecture this morning. So getting pretty quick as we approach the end of September. We've got a lecture this morning in a lab this afternoon that will be complementing some of the stuff that we've been talking about over the last couple of weeks. Last day, we introduced the idea of designing, or at least starting to figure out what the strength of our tension members might be for our braces, for example. The other day, we looked at a couple of expressions and we said, okay, well, when something's in tension, we're basically going to pull it apart. We can pull it apart in gross section yielding, right? So this was the expression that we used to calculate the gross yield resistance of the cross section. And we wanted to stop the brace from yielding because if the brace yields, it's going to stretch a lot, and that's going to take away the structural stability of our building when it's pushed laterally under wind, for example. We also looked at net section fracture. And one of the big differences here, despite the fact that they look similar in terms of the equation that we're using, here we're looking at actual fracture or complete breaking apart of the cross section where it's reduced to accommodate the bolts. And so we need to connect these things somehow. When we poke holes in our braces to bolt them to the gusset plate, we're getting rid of some steel. So the area is going to be smaller, but we let it yield locally a little bit because it's not really going to impact the stability of our structure. But once it reaches its ultimate breaking strength, there's nothing we can really do. And ultimately, we're going to lose all load carrying capacity, and there's not going to be anything left there to prevent the building from falling over. The other big thing here was that one is a ductile mechanism, the other is a brittle mechanism. When we're dealing with ductile failure of structures, we want that to happen, not that we want it to happen, but if failure is going to happen, we want it to be ductile. And so we had a different resistance factor, a slightly higher factor for yielding compared to what we had for net section fracture, right? We had 0.9 as a resistance factor for yielding, 0.75 for the net section fracture, because we want to encourage, if there is going to be failure, a ductile failure mechanism to develop. We looked at a very basic example, and I showed you a video of how some of these things can kind of work in terms of their net section fracture for a simple kind of tension member. And so we looked very quickly at a potential calculation, or a simple one, for calculating the net effective area for, they were just flat bar braces that had a couple of bolts in a square pattern. Today we're going to talk about how the net effective area can be different depending on the bolting arrangement. We're actually going to see today that there's more than one potential way that we could get net section fracture to develop through our bolt holes. Okay, so that's basically what we're going to be talking about today. When the bolts are arranged in a certain way, how does that change the calculation for our net area in tension? Okay, so the other day, introduced tension members, talked a little bit about net area. Today we're going to focus a little bit more on when it may or may not be different compared to what we looked at previously. For example, in lecture the other day, we looked at this situation. We had just a very, very simple pair of flat bar steel plates bolted to a thicker central plate. And you saw in the video, once it fractures pretty quickly, loses all load carrying capacity, and it tends to fracture across this net area through the bolt holes. And so the other day we looked at calculating what the net area might be for an example brace in that school across the river, and found that that was in fact the governing failure mechanism for that particular brace. This is a very simplified case. I would say most of the time, it's probably good practice to arrange your bolts in some kind of rectangular pattern. It's easier to fabricate, and it's easier to put together for the most part, and it's relatively simple to detail. From time to time, though, we may want to introduce something that's called a stagger in our bolt hole pattern. And the reason we might want to introduce a stagger is because if we do introduce a stagger, it's possible that we can actually increase the net effective area. So basically, we're moving potentially from a failure plane where we're getting rid of 2 bolt holes from a net area to a potential failure plane where we're only removing 1 bolt hole, right? So if it's hard to make this connection work, for example, we had a specific brace in the example the other day. Maybe we want to resist a load that was a little bit higher than the 580 kilonewtons that we were actually designing that flat bar brace for. And maybe the engineer didn't give me enough steel. Well, remember, the engineer basically tells us what this needs to be. They might say this is a flat bar 15 by 150. And then you got the flat bar to design a connection for, and if you can't make a rectangular bolt hole pattern work, you may introduce a stagger in an effort to increase that net effective area. Okay, so basically by doing this, we're just saying, okay, Wn in this case would be W minus a single bolt hole diameter, whereas in this case we have Wn is W minus 2 bolt hole diameters, right? So we can potentially increase the net effective area by staggering that bolt line up a little bit. The problem with that is not only do we have the potential to get rid of one of the bolt holes, we do also introduce the potential to have two different failure planes where if we're not getting enough area through this bolt hole here, it's possible that the stresses will actually want to go back through that back hole, even if it's not aligned with the original bolt hole. So here we've got basically one potential failure plane. So here we have one, and that's Wn is W minus 2 bolt hole diameters, dBH. Up here we have a blue one where we have Wn is W minus a bolt hole diameter. And then down here we've got an interesting one where, well, how exactly are we supposed to handle this situation? This looks a little bit weird, and it's not something that we've looked at yet. Okay, so today we're going to be talking about what happens when we start to stagger bolt holes. The motivation to stagger a bolt hole would be to potentially increase the resistance of net section fracture. But in doing so, we introduce new potential failure planes. And basically, it's our goal as the engineer to determine which of these failure planes is going to be the critical one. How is this connection actually going to fail through these two different failure planes? And when we have this stagger, how do we actually introduce new calculations to figure out what the increase in area might be? I have a little example here just in terms of those same connections that I showed you in the introductory lecture on Friday last week, with these different kinds of connections with different bolting arrangements. And I had one where we had the bolts arranged this way. I had another one where I actually arranged the bolts just in an opposite symmetric pattern. And when I pulled those apart, basically what happened was, for this bolt hole pattern where the two bolt holes were closest to load, we had the net section fracture similar to what we looked at the other day. But when we flipped the bolts the other way, we got a completely different failure pattern, right? There was a potential to fail this section through the first line up here. There was also a potential to fail the bolts through something that looked more like this. And so how do we handle these kinds of situations, and how does this change the resistance of our tension members? Basically, after today, you should be able to identify these different failure planes when we do introduce a stagger in our bolt hole arrangement. You should be able to calculate the net area for different identified failure planes. And basically, the main goal here is to identify the critical net section, right? We're basically going to say, here are these three potential failure planes. How do we calculate the net areas? Which net area is the smallest? Because that's where the stress is going to be the highest. And identify it and calculate the net section fracture capacity for that bolt arrangement for that particular tension member. Okay, does anyone have any questions about these three things, why they're important, or what this staggering of bolt holes business might be about before we get into the technical content for the morning? Cool. So like I said the other day, we introduced this expression. We've got a resistance in kilonewtons we're trying to calculate. And because we're trying to prevent this from happening more often than something that's more ductile, we're using a resistance factor of 0.75. This is not going to be changing for any of our calculations. If you have a specific grade of steel, the strength that you're using is not going to change. We're using 350W steel, FU is going to be 450, so that's not going to change either. The only thing that's potentially changing today is this net effective area that we're going to be calculating. And we'll see, we'll also continue to talk about net effective area next day when we introduce elements that don't have all the cross-sectional components connected. So when we're dealing with these kinds of connections, we actually have a new part here. The other day I only showed you for a segment normal to the force, net area is W net times the thickness. But when we have segments that are inclined to the force, and say that's when we have a stagger. We've got a stagger, we've got some segments that are perpendicular to the force, and we've got one that has an inclined section to the force. What we do is we calculate the same thing, pardon me, WNT. And so we calculate this as if there was no such stagger. And I'll show you what that means in a minute. But we've got the net effective width as if it was straight through, or the whole section was perpendicular to the force. But when we have an incline, we're going to add on this empirical term. You would like to think that when you have an inclined segment, the stress transformation kind of changes the way we do calculations, but we don't have any kind of stress transformation. This is actually an empirical equation that came from the early 1900s, and I don't know, we've had more than 100 years and we haven't found a way to do this any better than what we've been doing since basically the 1920s. So we add on this additional term that basically deals with the geometry of that stagger. We've got a gauge, whereas basically the distance between bolts perpendicular to the load. We've got a pitch, which is the distance between bolts parallel to the force. And this is how we're going to be handling these kinds of calculations. We might have one incline, we might have two inclines, and I'll show you some examples of where these might apply in different situations. But the one thing that I will say is that this works really well for simple connections like the flat bars that we've looked at so far. W is pretty straightforward. We don't have to do any kind of fancy calculations. When we start looking at hot rolled sections, it's going to be annoying to try to do WNT plus all this S squared T over 4G stuff. Basically, if we're looking at hot rolled sections, we already know what the full area is. And so we're not going to be dealing with calculating the width times the thickness for all the parts of our hot rolled sections. We're just going to start with the gross area that we know we already have that comes from the handbook. We're just going to subtract the number of bolt holes that we get times the thickness of the bolt holes from the cross section. And then we're going to add in this business S squared T over 4G. The way it's written in the handbook here isn't necessarily as clear as it should be. In fact, it's a little bit vague. And so when I present it here, I include the summation sign. All right, this is to account for the fact that there could be potentially more than one stagger. And so we're going to add the sum of the staggered components. If we have 2 or 3 staggers, for example, we need to add on the individual components dealing with that stagger that increases the net area. And I'll show you a couple of examples here of where we might apply this. So basically on the left-hand side, it's a pretty simple stagger. We've got what would have been a rectangular set of holes, but it's just moved up. The right-hand side is moved up by some distance S. We call that distance S the pitch. Okay, so whenever you see S, you can just look at the slide. The most difficult thing to remember is which of these two things should be S and G, right? When you're saying, okay, well, I know it's S squared T over 4G. Which of these dimensions is S and which is G? If you forget, you can just come to this slide. S is the pitch, which is the spacing between the staggered lines of bolts parallel to the load. And gauge is the distance between the bolts perpendicular to the load. So basically, in this case, how we would apply that equation is we'd say, okay, AN is WNT plus S squared T over 4G. And what WN is just simply W. In this case, we can say this is W minus, and we're going to take out the diameters through which we pass on that potential failure plane. We're going to say, okay, this is the potential failure plane going through these 2 bolts. We're going to subtract 2 bolt hole diameters. Again, that's as if it was just as if the bolts were not staggered at all. This WNT part is as if these bolts were just on a straight line. We don't augment it at all to account for the fact that we have this stagger. But then we add on this S squared T over 4G term. So basically we have the net area that we would have had if it was a rectangular set of bolts, plus the additional area that we might get from staggering those bolts by a pitch S. Does anyone have any questions about that left-hand side, how we might apply that summation term of the WNT plus S squared T over 4G, how you might calculate WN in this case, anything about what we just went through for adding on the additional area for staggering, how it might apply to this single staggered segment on the left-hand side? Okay. The right-hand side, similar, but a little bit more complicated, not that much more complicated. Pardon me. So in this case, we're saying, well, there's a potential failure plane here that's going through the 3 line of bolts, or the 3 bolt holes. And so basically we're saying, okay, we're passing through 1, 2, 3 bolt holes. Again, AN is going to be WNT but we're going to have plus the summation of S squared T over 4G. Wn, again, we calculate Wn as if these bolts were not staggered. We're basically going to say, okay, if these bolts were not staggered, then we'd basically have, a Wn that goes through these 3 bolt holes. So for us here, maybe I'll just erase this to make a little bit of space so I can write out a little bit more here. Basically, we're going to say that An is equal to W, but in this case, it's minus 3 bolt hole diameters multiplied by the thickness of the plate, plus we're going to have S1 squared T over 4G1 plus S2 squared T over 4G2. Okay, so again, it's important that we remember here when we're doing the WNT part, Wn is calculated as if there was no stagger, and so we just take away the number of bolt holes we cross through away from the gross width of the plate. Then to account for the fact that we've got these 2 staggers, we're going to add on the individual components S1 squared T over 4G, S2T over 4G. And that's how we're going to calculate what the potential area might be for that potential failure plane. Okay, does anyone have any questions about what's going on here? We've got an equation to calculate net effective area for some simple flat bars. We're passing through holes, and so the WNT part doesn't change. To account for the stagger, we add on an S squared T over 4G, depending on how many inclined segments we're developing potentially along that failure plane. Does anyone have any questions about those ideas and how we might apply them to perhaps a different scenario? Katie.
So on the left side, it's 2 bolt hole diameters because we only have 1 S and 1 G.
Well, it's not 2 bolt hole diameters to deal with anything to do with the stagger. It's just simply because that's the number of bolts that the failure plane passes through, right? So we're failing this across 2 bolt holes here, right? And so that's where the 2 bolt holes is coming from. We're subtracting those 2 bolt holes because the steel's gone because we've drilled it out to accommodate the bolts. Over here, we've drilled out 3 holes. And in that case, when the failure plane goes through each of those 3 bolt holes, then we're going to subtract each of those bolt holes from the net width when we're doing that calculation. It just happens here that we also, yes, in this case, have 2 staggers where we have 3 bolts, 1 stagger where we have 2. That doesn't have to be the case. There are other arrangements where you can have a stagger but still go through 3 bolt holes. Okay, any other questions?
So that particular failure plane is for those 3 bolts arranged like that?
Yep, just for those 3 bolts arranged like that for a failure plane going through those 3 bolt holes. And I'm going to elaborate on that in a minute. Okay, anything else? Okay, so when do we have to account for stagger? I think it's obvious when you have to account for stagger if the bolts are not arranged in a way that looks something like this. And so if there's no pitch of one line of bolts or one bolt relative to another, we do not have to account for stagger. And the other interesting thing is that if we don't have stagger, there's only one way this thing is going to break apart. There's no other way that we can pull this apart other than by fracturing it through the first line of bolts that are closest to the load applied. Basically, what we expect to have happen when we have a rectangular set of bolts is it gets pulled apart across the last line of bolts. And the reason for that is because steel is ductile as it approaches the ultimate strength, we're basically going to be assuming here, as we talked about in Lab 1 when we looked at the bolts in double shear or single shear for that problem on assignment 0, we're basically going to be assuming that these bolts all carry the load equally. And so here we might have a factored tension force, so 1.4 wind plus some other notional lateral loads or something like that. And we're basically going to assume that we have TF over 4 here, TF over 4, TF over 4, and TF over 4. And if that's the case, if we look at a section back here, basically the stress that's going to be on this component or going through this last line of bolts, if we draw the free body diagram, we have TF over 2 pulling to the left. So the stresses through this net section at the back furthest from the applied load, those stresses are going to be half what the section experiences at the net section closest to the applied load. Okay, so here we're assuming that the bolts share the load equally. And so by statics, there's no other cross section on this area that's going to have a higher stress than the one that's closest to the applied load through the first row of bolts passing through there. For example, we're also not going to get something like this happening because we have TF over 4, TF over 4, TF over 4, and TF over 4. Basically, on this section now, we basically only have 3 TF over 4, so we have 3/4 of TF, which is more less load, and we're increasing the net area because on that failure plane we'd potentially have a stagger. And so there's no way here that we're going to fail this plate through a staggered bolt arrangement where we miss a bolt and go back to the back one, because this bolt, we've lost the load that gets passed through this bolt here, and the area goes up. The stress is smaller, but the area is higher. That's not going to be a critical net section. We do not need to check something like that. Okay, so when we don't have staggered bolts, we only have one failure plane, and it's through that first line of bolts, the one that's closest to the applied load over here. That's where the area is the smallest and the stress is the highest. When we start to increase a stagger, and this is not the best detailing, but it's nice to show academically what goes on here. Now we've got a single bolt hole, and it's hard for us to necessarily determine what's going to happen here. It's possible that we'll get fracture through that first bolt, and that would be consistent with what we've talked about before. In this case, we have TF, and we have TF over 3, TF over 3, TF over 3. Okay, so the bolts are sharing the load equally, and so that means the total force on this cross section is TF. We have TF over 3 on the other side, and we have a potential failure plane through that line of bolts. And we would calculate this as AN is W minus a single bolt hole diameter T, and that's it. We have no stagger on that particular failure plane. It's possible to fracture the plane straight through that perpendicular section. We have one bolt hole and a perpendicular section, but it's also possible that we might fail at something like this, where now we're passing through 3 bolt holes. So our net area gets reduced because now we're passing through 3 bolt holes, but we have stagger, and so the stagger is going to increase our net area. So here, if I called this S, and if these were both G, let's just assume that G and S are both the same for both of these staggers here, my net area would be W minus 3 bolt hole diameters times T plus 2 S squared T over 4G components. Okay, so this area, we don't know until we do the calculation if it's going to be bigger than the one that we looked at on the previous slide, because we're removing more bolt hole diameters, because this is a plane that would go through more bolt holes, but we're also increasing it because of the stagger associated with the incline segment between the first bolt and the back 2 bolts. Okay, so basically we're saying, well, we're taking away 2 more bolt holes, but we're increasing some stagger. In our case here, we actually have to calculate this area. This might be AN1, for example. And we have to calculate this one. It might be AN2. And the failure plane that's going to be most critical is the one where the area is the smallest. Because when the area is small, the stress is higher, and we're going to more likely to get failure on that particular failure plane. Likewise, it's possible, I don't know how possible it is, but you'd have to calculate this. It's possible to get a slightly asymmetric failure plane. And so in our case here, now we've got just the failure through 2 bolt holes. So we might say AN3 is equal to W minus how many bolt holes for this particular case? 2. 2 bolt hole diameters times T. And in this case, we just have the single stagger on this failure plane. This is G. This is S, so we have plus S squared T over 4G. So in our case here, there are 3 potential ways, and I mean, technically, if G and S were different for the other incline, there might be 4 potential ways for this thing to actually pull apart on the net section. And so it's important that we understand, first of all, how to identify how we're going to potentially develop failure planes through each of these bolt holes, how many different failure planes we could have, and how to quantify the net area associated with each of these. Basically, the secret is you never want to consider a failure plane where you still have a bolt that's basically attached to the piece that's pulling off, because that reduces the load acting on the remaining portion, and that therefore reduces the load acting on the net section, and the net section almost always gets bigger. So a bigger area, smaller load, you know intuitively that that's not going to be a governing failure mode. A failure mode is one that can pass through any of the bolt holes as long as there are no more bolt holes attached to the piece that's getting pulled away. Okay, so in this case here, this is a potential failure plane. We go through one bolt hole. This is a potential failure plane where we go through all of the bolt holes. And this is a potential plane where we go through two of the bolt holes, but never do we have a bolt left over on the piece that's getting pulled away. You should be able to cut this piece with some scissors through the holes and not have any full hole left on the piece that's getting pulled away from the applied factored tension force. Does anyone have any questions about why these three pardon me, failure planes are something that we should be investigating, or how we would calculate the net area associated with either or any of those three potential failures? Wow.
What would happen if one of the bolts pulled away with the other piece? What would be the significance of it?
It wouldn't. That's the significance of it for the most part. It's very, very unlikely. So what I would say is, like, basically what's going on here, especially like for most simple applications, like if we imagine what's going on here, it is possible, and I've actually done this before, because if you're bad at drilling holes, it is possible, for example, that we don't actually share the load equally. Like if one of the holes is like really tight and the rest are loose, you're basically going to fail that bolt first, and then it's who knows what's going to happen. But any professional detailer knows how to drill stuff and put stuff together. And so basically it's not that what would happen if this was the case, it's more that this could never be the case, right? So basically if we look at, we've got 1, 2, 3 bolt holes, or 3 bolts worth of load on that net section. And so the tension force here is basically 3/4 or 75% of the factored force, right? So we have 75% of the factored force acting on a cross section that's by definition bigger, right? And so both the fact that we're reducing the load and increasing the area, I mean, yes, well, I guess, yeah, in this case, like compared to this, AN is W minus 2 bolt hole diameters, T. And then over here, AN is the same thing, W minus 2 bolt hole diameters times T plus S squared T over 4G. And so we have the addition to the net area of S squared T over 4G and the reduction in the load by 25% acting on that cross section. It's just not physically something that we would have to check, because it's not physically something that would happen to that connection. Anything else? Any follow-up? Okay. So with that in mind then, a fun pull everywhere question, or at least one that I think is fun, just to try and hammer in what we just talked about for, well, 20 minutes or so. Which of the 4 options here for this particular connection is not a potential failure plane? Because if you cannot identify which one's not a potential failure plane, first of all, you're going to be wasting your time doing these kinds of calculations. And second of all, you're going to get the answer wrong. This one always makes me feel happy. Nobody picks any of the other options, except perhaps that one. I think there's a joker in the class somewhere. Yeah, so I mean, the majority here is going towards the bottom left here, option C. Does anyone who picked option C, pardon me, Jesus, feel comfortable sharing why they selected C instead of A, B, or D? Okay.
C has one bolt hole above, so we just said that that's not very likely. So we don't use that for right now.
Exactly. I just said that that's not something we should be looking at. Basically, the reason is back here, I mean, yeah, I mean, we've got 2 bolt holes. There's not very much stagger. I mean, the net area might be plus or minus 5 or 10% to the others, but on that net area, we're losing 1/3 of the load, right? So we've got TF over 3, TF over 3, TF over 3. This one has TF over 3, and so if we try and pull apart something back here, on that failure plane, there are only stresses associated with 2/3 of the factored force. and the area is more or less the same. There's no way that that's actually going to happen. What's more likely to happen is we have the stresses associated with the full factored tension force on these three different areas that may or may not be easier to figure out in terms of what the associated net stagger would be. The next question I might ask, and I guess I've never really asked this before, it's not obvious if A would be better or worse than B or D. Is there any way to tell whether or not B or D might be more critical? Let's assume that like the gauge distance for both of these bolts is similar or the same. If the gauge distance, the distance between the front bolt and the left bolt and right bolt, parallel or perpendicular to the force are the same, is there one between B and D that's more likely to develop than the other one? Well, we can go back here to, whoops, what am I doing here? We can go all the way back to this slide. And if I get rid of some stuff, we're basically looking at more or less this one over here, right? It's very similar to this, pardon me, situation. And so let's just say G1 is equal to G2, and here S1 is obviously bigger than S2, right? And so just like our pull everywhere question here, similar in terms of what's going on. And basically what we're comparing potentially is the blue one, which passed something like this, to the green one, which passed something like this. Is the green one or the blue one going to have more net area? How do I figure it out? Well, for both of them, AN is going to be W minus 2 bolt hole diameters. Plus, we're going to have either S1 squared T over 4G, S1 squared T over 4G, or S2 squared T over 4G. So this is going to be the same for both of those planes. But then we add on either S1 squared T or S2 squared T over 4G. Which one's going to result in the bigger area? S1 squared, right? Because G is the same. S1 squared T over 4G is going to be bigger. So that makes it more likely that S2, or the green failure plane, will have a smaller net area, okay? So if G1 and G2 are equal here, you don't necessarily have to check the blue pattern, but you do need to check the green pattern. And again, if you can't identify that, that's fine. But you should be able to look at these two and say, okay, the net area in terms of bolt hole reduction is the same, but I get a bigger stagger on the blue side than I do on the green side. That means that the green side here is going to have a smaller total net effective area. Are there any questions about that? Yep.
How many percent net area failure in this case? If G is equal but S is different, will it be 3 or 4?
How many do you think there are?
3.
You think 3? So I would agree if we just went through the process of elimination that we just did, right? So we basically more or less eliminated the blue area here if G1 and G2 are equal, because S1 is going to be slightly bigger. In addition to that, there's going to be the potential to fail it straight through that first line of bolts, in addition to the potential to fail it through all 3 bolts, right? Something like this, right? So including the blue and green together, we also have the red and the black. There are 4 potential failure planes here. By elimination, if G1 and G2 are equal, we could get rid of the blue one. Or if S1 and S2 were equal, we would base it on which one had the smallest G value, right? So if G1 is different than G2 and S1 is different than S2, here we've got 4 potential failure planes on the right-hand side. Over here on the left, just to perhaps provide some completeness, we've got potential failure plane there, and we have potential failure plane here. And so on the left-hand side, we just have 2 potential failure planes introduced by that single stagger. So for symmetric stagger, basically every stagger introduces one new potential failure plane. But if the gauge and pitch are different, there's the potential to add more than one. Okay. Well, let's see if we can put this into a more practical context. If we revisit the example that we did the other day, where we were looking at this brace and its connection for that building across the river, we might remember that we had a flat bar 15 by 150 that had a factored tension force from the structural analysis results of 580 kilonewtons. The engineer of record would put 580 kilonewtons on the drawing, send it off to the connection designer. They said, we picked 15 by 150 flat bars, we need to make the connection work. And we had 8 bolts that were 5/8 inch, and they had a certain pattern. In this case here, let's just say they were doing all this work and someone opened up the new building code that's going to be coming out soon. So for example, for us, that might be MVC 2025. And there's no onus on anybody to say, okay, well, there's this new building code coming out, and so we've already designed this, we have to change it for the new building code. That's never the point of updated building codes. But let's just say we had an engineer who was looking forward a little bit and an owner who was, a little bit more industrious and conscientious in terms of their building. And the engineer basically found that in Appendix C, the wind loads basically resulted in an increase of this factored tension force just by a little bit, like 6%. The owner might say, what do I need to do? The answer is nothing. You don't have to do anything because that building code's not enforced yet. But perhaps it will make it easier for you to sell the building for reuse in the future if you were to address that increase in the wind load now. And so the owner is forward thinking, and they're saying, okay, well, the engineer has already picked this brace. I can't do anything about that, and I've already paid them, and it's already with the fabricators. We're going to go back and do a lot of rework. The fabricator's engineer suggested, well, the flat bar, right, when we did the VAGFY calculations, it's got lots of gross section yield capacity. It was 709 kilonewtons. It's not gross section yield that's going to be governing the design of the brace. There's lots of capacity there, even for an increase of 6%. What we could do, since we only need this little bit, is we could stagger the bolts, right? You can get a little bit more net area potentially from designing a connection this way. And so the question today is, let's figure out if staggering the bolts by, I guess in this case here, as much as 45 millimeters, is that going to give us enough additional net section fracture capacity for us to resist this additional 6% compared to what it was originally designed for? Okay. Does anyone have any questions about what I'm trying to get at with this example or what this example is asking us to do? Okay, so again, I'm going to turn it over to you for 5 minutes or so. This side of the room, I want you to, or no, that's not what I want to do. First, this is what I want you to do. I want you to talk to the person next to you or think on your own if you're more comfortable thinking independently. What I want you to do before we get into any calculations here is see if you can identify the potential failure planes that would be acting through this example connection before we start calculating some potential net areas. Okay, so with the person next to you, think about it. Call someone at home if they're just getting up and they didn't want to come to steel design class. You can give them a call and say, hey, we're working on this. Do you think you can help me out? I want you to identify the potential failure planes so that we can calculate their net areas. Okay, has anyone identified at least one potential failure plane? You want to draw it on the example? Draw me just one potential failure plane. Does everyone agree that that's a potential failure plane? Excellent, thank you. Has anyone identified a second one? No, I'm walking around with the iPad, everyone's sheepish, right? Does anyone want to draw the second potential failure plane? Sure. Oh, hold 1 second. I'm going to change the color so everyone can. There we go. All right. Does everyone agree with that one? Yeah. Excellent. Has anyone found any additional failure planes? The answer should be no. There are two potential failure planes here. There's one through the first bolt, and there's one through the first two bolts on a stagger. Okay, so we've got two potential failure modes to consider here. We've got the green one, we'll call 1, and we've got the blue one, we'll call 2. And what we need to do to determine what the net section fracture resistance is going to be is calculate AN1, calculate AN2, and determine which of those two is going to be more critical. Okay, so here I'll take over for the rest of this one. We'll go into this now. So we're going to look first at AN1 for the first potential failure plane. AN1, we'll always write it out as WNT plus S squared T over 4G, or the summation of them. Do we have a stagger on potential failure plane 1? No. That's 0. How many bolt holes did we pass through? 1, right? Math is not hard. It's how you apply it that can be difficult. So basically, we just have WNT. Our WN is 150. Or sorry, our gross width is 150. W is 150. We're subtracting 1 bolt hole diameter. Does anyone remember what the bolt hole diameter was from class the other day? Drilled, it was 17 millimeters, right? I'll just maybe write this here. DBH is 17 millimeters. That comes from the handbook for 5/8 inch bolts with drilled holes. Minus 17 millimeters multiplied by T, which is 15 millimeters. Our net effective area here, if someone wants to do that calculation, that'd be helpful because I have yet to open up my solution sheet, apparently, for that one. And I'll give you an opportunity to practice doing calculations like that on your calculator. Can you repeat that a little louder, sorry, Katie?
1,195.
1,185?
995.
1995. That sounds familiar. I'm pretty sure I remember that number. Yeah, 1995 millimeters squared. Okay, does anyone have any questions about that calculation, what numbers went in it, or how we got that number? Okay. AN2. How many staggers do we have? 1. How many bolt holes do we pass through? 2. It sounds like a kindergarten class. 1, 2, 3. Joking aside, we have, again, WNT plus sum of S squared T over 4G. We just have the 1 stagger here to consider. Our WNT is similar, but with 2 bolt hole diameters omitted. So we've got 150 millimeters minus 2 times 17 millimeters plus S. I had said that the stagger overall was 45 millimeters, or half 90. Which here is S and which is G? What number do I use for S and what number do I use for G? Well, if you forget, you can go to this slide. S is the 45 millimeters, or the distance that the bolts are staggered by, parallel to the load. And G is the gauge, which is the perpendicular distance between the bolts. So here, this is G, is 80. This is S, which is 45. So I'm going to add on 45 millimeters squared, all times T. Oops, I missed the 15 millimeters here, sorry, times 15 millimeters. This is also times 15 millimeters, but divided by 4 times 80 millimeters. Right, so here we're subtracting one more bolt hole. Right, so we're reducing the area by the extra bolt hole, but we're also increasing it to account for the stagger. So it's not immediately clear before we do the calculations which is going to be larger. I'll let somebody do that calculation. I have the number here, but it's good to practice doing these kinds of things on your calculator. Does anyone have an answer for that?
In the first example, why did we deduct only one bolt hole? Couldn't it be two?
In the first one, we only deducted one bolt hole because the way that this would rip apart is just through that one bolt hole, right? So in our case here, it's possible that we'd pull this piece away by breaking it through that net section, and on that net section, there's only one bolt hole, right? Because basically here for the green one, what we do if we pulled this away is it would look something like that. So we're only subtracting the one bolt hole diameter. The original design was not staggered. And in the original design, we did minus 2 bolt holes. Right? So I also get 1835 millimeters squared. Okay. So potential failure plane 1, 1995 millimeters squared. Potential failure plane 2, 1835 millimeters squared. Which of these areas do I use to calculate the resulting net section fracture resistance? Bigger one or the smaller one? Smaller one. Smaller stress, smaller area, higher stress. The same load is present on both of these areas. And so this is going to be my critical net area. And that's the one I'm going to use to calculate the net section fracture resistance. Okay, so, whoops, that's what I want to write. We still have a problem to figure out here. We're updating our net section fracture resistance, VU, ANE, FU. Again, here we just got flat bars. Whenever you have a flat bar connected by bolts, the ANE is equal to AN. We'll talk about other situations on Wednesday this week. But for now, we've got 0.75 times the critical value, which is 1835 millimeters squared, times FU, which is 450 MPa. I get a net section fracture resistance, doing that calculation, of 619 kilonewtons. What did we have the other day? Is that bigger than what we had the other day when we didn't stagger the bolts? The other day, when we didn't have stag bolts, we had a resistance. We'll compare this to the old TR, which is 587 kilonewtons when we did not stagger the bolts. And so we got a resistance increase, right, by staggering the bolts by that 45 millimeters. And if I was trying to figure out what that is, 619 over 587, that is a 5.4% increase in the net section fracture resistance. Now, thankfully, we're trying to make up 6% difference, but TR was already a few kilonewtons bigger than what it needed to be. So let's figure out, for example, what the new TF value would be. TF before was 580. We're increasing that by 6%. 580 times 1.06 is 615 kilonewtons. So we only increased our resistance by 5%. We needed 6%. Thankfully, we already had 7 kilonewtons more than we needed, so that helped us. Is the connection designer achieving his objective of increasing the resistance to an acceptable level so that the owner can feel happy that their building will satisfy the requirements of the new building code they wanted it to? Yeah, we've got more resistance than we will have in terms of a factored effective force in that brace. We've got 4 kilonewtons more, again, kind of threading the needle. But remember, this is a reduced resistance. It's artificially small. We've taken 25% off of the actual net section fracture resistance we expect. The load here is factored up, so perhaps a load factor of 1.4 on wind and some other load factors on notional lateral loads. So we're saying TF is less than TR, and therefore that's acceptable. Okay, does anyone have any questions about what that example was going for, what we did, and how the stuff we talked about in lecture leading up to that point got factored into the example today? All right, well, those are the important things then. You should be able to identify potential failure planes through bolted connections with staggered bolts, calculate the net area for different identified failure planes when accounting for the staggers. Most importantly, identify the critical net section and calculate that net section fracture resistance. Does anyone have any questions about anything that we've talked about this morning before wrapping lecture up? All right, we'll see everyone this afternoon then in lab.